Today's air drilling industry is competitive. Drilling faster at lower total cost is critical for continued success of the drill contractor and the companies they drill for. This video will focus on boosters in a mineral exploration, reverse circulation application. But the concepts discussed here will work in any air drilling situation using down-the-hole hammers. Let's see how booster compressors for high-pressure down-the-hole hammer drilling can add to your bottom line. A booster adds additional stages of compression and cooling to the primary rig air compressor. The booster only increases pressure in the system. If additional air volume is required on a job, an auxiliary compressor is added. All major down-the-hole hammer manufacturers have developed tools capable of operation at pressures of 350 to 400 psig across the tool. Energy must be provided by the compressed air to drive the hammer piston into the bit so that all the buttons on the bit actually crush the material being drilled on every blow. Lower pressures at the tool will result in small cuttings, slow penetration, regrinding, higher drill string torque, and premature hammer wear from high friction temperatures. Using booster compressors to maintain proper air pressure at the hammer directly affects profitability. Booster compressors help maximize penetration rates and improve the life of consumables, providing fewer trips in and out of the hole. Better safety due to reduced rod handling, along with decreased overall project costs through more distance drilled in a given time, are also major advantages. To optimize the drilling operation, we must provide the drilling process with the amount of energy from compressed air to get the most work done. We can look at this process in more detail to identify the pressure losses and see how a hurricane booster compressor can keep equipment working as designed and the drillers productive and profitable. To work through a typical application of a booster compressor in down-the-hole hammer drilling, we must know the following factors. Let's assume the target depth is 720 feet. The approximate water table is 200 feet, and we have some basic idea of the rock strength on the way down and at the bottom of the hole. Here we must decide from experience the minimum air pressure required to work economically at the bottom of the hole. Friction loss across the hammer depends on the hammer design, the air volume it consumes, the inlet pressure and back pressure. In this case, minimum pressure drop across the hammer will be 280 psig. A 4-inch reverse circulation drill string will be used to provide a 5 1/4 inch hole at the surface and a 4 3/8 inch hole at the target depth. Friction loss occurs between the booster discharge and the inlet of the hammer and must be overcome before any energy becomes available for drilling. For this exercise, we've already determined the minimum amount of 280 psig. In this example, we'll use two 50-foot lengths of bull hose with an expected loss of 5 pounds pressure. Losses through the rig air valve and air swivel total an additional 5 pounds of loss. Pressure drop down the annulus of the 4-inch drill string to the hammer inlet is the major consideration here, since it increases with hole depth. We allow 1 psig loss per 13 feet of depth for a total pressure drop of 55 pounds in this example. The hammer check valve accounts for an additional loss of 2 psig for a total pressure drop of 67 psig before the inlet of the hammer. Pressure loss also occurs from the outlet of the hammer as it vents to the atmosphere. As we've determined for this exercise, our target depth is 720 feet. We encounter water at a depth of 200 feet. The height of the water column is 520 feet. The pressure required to overcome the hydrostatic head is 1 pound for every 3 feet of water, which equals 173 psig. Friction loss in the 2-inch inner tube of the double wall pipe is 1 pound per 9 feet for a total of 80 pounds. The head assembly loss is 5 pounds, and we also have a pressure drop of 10 pounds across the cyclone vent. The total loss from the hammer to the atmosphere, therefore, is equal to 268 psig. Total losses before any useful work can be done at the bottom of the hole will be the sum of the losses before 67 and after the hammer 268 for a total of 335 psig. To get the minimum acceptable pressure to drill this hole, we must add the 280 psi-G required by the hammer to the total loss external to the hammer. The total pressure required is thus 615 psi-G. Now we calculate the volume of air required. For the hammer to operate successfully, the chambers above and below the piston must be filled with compressed air on each cycle. As air pressure increases, the volume of air required by the hammer increases directly. Twice the pressure needs twice the volume to do the same work in the hammer. We can use the table supplied by the hammer manufacturer to indicate the volume of air consumed by a particular hammer. If the table showed a need for 700 cubic feet per minute at 300 psi-G, in our application, the same hammer would require 615 psi-G divided by 300 psi-G times 700 cubic feet per minute, or 1,435 cubic feet per minute at the target depth. If the volume required is greater than the capacity of the primary compressor, the use of an additional or auxiliary compressor is necessary. On the drill site, you'd begin your hole with your 350 psi-G primary air and note the penetration rate. As drilling progresses, the air pressure and air volume can be increased to maintain constant penetration rates. The increasing pressure by the use of the booster is merely offsetting parasitic losses. The increasing volume, possibly with use of an auxiliary compressor, is required to fill the air chamber in the hammer and to maintain air velocity to move chips up the drill string. Before drilling with a booster compressor, follow these safety guidelines. Because you use more air volume at high pressure, make sure that you increase the amount of hammer oil in direct proportion. Audit all hoses and connection from booster outlet to air swivel inlet for pressure and temperature rating. Make sure the air swivel is rated for the maximum pressure that can be supplied by your compressors. All flexible hoses must be restrained at both ends with whip checks. Check rating, correct function, and all fittings in the oil and water injection circuit. Check all relief and check valves. Check emergency shutdowns and engine and compressor protection systems. Make sure everyone on the site can shut down the rig and the auxiliary systems in the event of an accident. Have fire extinguishers on the rig, as high-pressure air leaks support combustion of flammable material. Make sure drill pipe, its inner tubes, and all O-rings are in good order. Use crews trained in safe operation of the rig. And wear protective equipment: gloves, eye and ear protection, hard hats, and work boots. Air drilling using a hurricane booster compressor can greatly enhance your drilling operation. You will achieve quicker drill cycles, better samples, less wear on equipment, and an overall reduction of in-hole problems. Hurricane Compressors manufactures a wide range of booster compressors. Single and multi-stage boosters are manufactured with flow rates up to 2,500 cubic feet per minute and a final discharge pressure up to 2,500 psi-G. We hope this video has proven useful and informative. Hurricane Compressors can be reached at 317-736-3800 by phone, 317-736-3801 by fax, or write to us at 1015 North Hurricane Road, Franklin, Indiana, 46131. Ian Spear, Projects Manager for Air Drill in Perth, Western Australia, developed the material presented here. Air Drill is a Hurricane Compressors booster master distributor. Hurricane acknowledges his efforts and thank him and Air Drill for their support and help.